Hello, everyone, and welcome. This is topographic mapping at a grand scale as part of WGI's webinar series. My name is Mark Topping, and I'm excited to share with you some project results today. It was suggested to me that we call this webinar Topographics with Topping, but A, it's a little cheesy for me, but B, it's really not about me. It's about sharing our knowledge and our experience with elevation mapping using wide area lidar collection. And it's about a really interesting project that WGI executed over the Grand Canyon. Not only is it a good example to share a little bit about the technical knowledge that we have in airborne lidar for elevation mapping, but also it's a great project use case that demonstrates some of the challenges with collecting wide area lidar in an area where elevation changes so drastically, and on a large scale project from the project management perspective, which requires a great degree of upfront planning and coordination. Before we get going today, I'd like to remind you all that this is a follow-up webinar to a white paper that I authored, which was released several months ago. If this is of interest to you or you'd like to learn a little bit more, you're more than welcome to reach out to WGI or myself, but you can get the white paper on WGI's website. So if you have any trouble, please feel free to reach out. Secondly, for anyone out there who is able to self-certify for continuing education credits for any professional certification, please feel free to reach out because we're willing and able to provide a certificate showing that you participated in this webinar. Again, you can reach out to WGI directly through the website, or feel free to reach out to me at mark.topping@wgigeospatial.com. That's mark, mark.topping @wgigeospatial, one word, .com. So let's kick it off. So who is WGI? WGI is a multidisciplinary consulting and engineering firm based out of West Palm Beach, Florida. We have a number of divisions and we operate nationwide. We specialize in transportation engineering and design builds. We do civil engineering, we do buildings, we provide environmental services. But our geospatial division is actually our largest and the one that I am a part of. Our geospatial division provides a wide range of field collection and data processing and product generation from a single source. Again, we operate nationwide and we have 160 geospatial professionals over 9 states and 23 offices. Our geospatial division collects data from subsurface for subsurface utilities, all the way up to land survey, 3D modeling using static lidar. We do BIMs, we do interior scanning, we do terrestrial mobile lidar throughout the country for utilities, for roadside assets, for inventory of and asset management. We do vegetation management as well. And we provide services all the way up through survey and UAS collection. Now, in 2022, WGI acquired a firm that I was part of that specializes in wide area mapping for state and federal clients using the latest and greatest airborne remote sensing technology. We hold several state and federal contracts, and we have a deep history of performing lidar services for elevation mapping like the one we're going to cover today. So again, this is a graphic that shows the diversity in WGI's services. We're a one-stop shop for subsurface terrestrial, kind of going left to right. We're showing our ground penetrating radar, our terrestrial mobile lidar, our backpack scanning. We do sidewalk assessments. We're showing our vac trucks and our SU services, our UAS collection, and we also do hydrography. We have several hydrographic vessels and hydrographic surveyors, as well as H&H modeling and flood forecasting. But up in the top right, you have our fixed wing aircraft, which is near and dear to my heart and the service that I'm going to be covering today. So through one of our federal contracts, WGI has collected almost 300,000 square miles of elevation data for public consumption. The map on the bottom left is showing our quality level 2 lidar acquisition history in green, and we'll get into what quality level 2 means in a little bit. And quality level 1 is shown in orange. You'll see the Grand Canyon National Park project highlighted with this red circle. And I would break down airborne lidar mapping into sort of 4 categories just to kind of show the area that we're going to be focusing on today, which is wide area mapping. So on the graphic on the right, you're seeing a larger survey aircraft with a long-ranging lidar sensor. Typically, we fly higher for elevation mapping because the key is to collect large areas efficiently and cost-effectively, and that's something we do. If we fly a little bit lower, we can collect higher spatial resolutions and higher accuracies with engineering grade surveys. For corridor mapping for, say, utilities and transportation infrastructure, our preference is to leverage and integrate a hybrid data set of our fixed-wing aerial lidar collection, typically for soft surfaces, as well as our terrestrial mobile capability, which provides higher resolution and higher accuracies on transportation and utility infrastructure. However, we've also collected using helicopter and low-altitude helicopter flight. And the very right, WGI also has experience with doing bathymetric lidar surveys along coastal and intercoastal and riverine waterways. We have 3 of the latest and greatest topo lidar sensors from Teledyne Geospatial, the Galaxy T2000. What you're seeing in the bottom right is a unique integration of 2 of these Galaxy topo lidar units co-mounted on a single sled and slightly pitched so that we can collect the sides, sort of a semi-oblique collection. We can collect the sides of features for better extraction. The G2 is a unique sensor because it offers the highest pulse resolutions of any topo linear mode lidar system that's available on the market today. Each sensor collects 2 million effective pulses per second. So the sensor is effectively collecting 4 million measurements per second, which is quite unique and useful in extraction and wide area mapping. So here's our first sort of technical sidebar where we'll step away for a minute and cover why and how elevation mapping is useful from a national level. And I'm gonna introduce you for anyone who's not already aware to the 3D elevation program, or 3DEP. This is a congressionally funded national baseline data set of high resolution lidar and elevation products. And it's derived from quality level 2 topo lidar or better. As you can see in the top left graphic, that's the 3DEP quality and age by collection year. So as you can see, the lower 48 are almost entirely covered with a national baseline elevation data set. Now, why is that useful? Why is that so important? I'm going to quote the United States Geological Survey, or USGS, who say that 3DEP data for the nation informs critical decisions that are made across our nation every day that depend on elevation data. This ranges from immediate safety of life, property, environmental, to long-term planning and infrastructure surveys. So even as a private consultant ourselves, we use, whether we collected it or not, we use 3DEP data all the time in providing additional products such as building footprint extractions from the LiDAR, or we can use it as a comparison data set to new geospatial collections. For example, we can look and see first floor flood elevations or finished floor flood elevations against a high resolution, quality assured data set where we're quite confident within a specific degree of accuracy that is well defined where these elevations lie. Another useful sort of spin-off, now that we're nearing completion of elevation data for the entire country, coast to coast to coast, we're moving towards using this elevation data in other applications. Now that the data is collected, you'll see that we're moving towards elevation-derived hydrography as one example of how 3D elevation data may be used, particularly to understand flow and accumulation of water and addressing water networks across the United States. We call that the 3D hydrography program, or elevation-derived hydrography. And that's kind of one example of the usefulness of this data. 3D data is publicly available for anyone to download through the national map, as well as other federal portals. This data is procured and quality controlled through USGS using the well-defined lidar base specifications, which is updated regularly. And they have pre-qualified service providers. WGI is one of them, who can collect data to a predefined standard. It's so that stakeholders can be assured that qualified and experienced firms are performing this work. A data collaboration announcement, or DCA, is the process that allows multiple state and federal government stakeholders to collaborate and jointly fund new LiDAR projects. And even though we have a baseline of quality level 2 LiDAR, we're seeing refreshes, obviously temporally, topography changes. So updating this LiDAR data is still of concern, and also improving that existing LiDAR data to a higher standard, such as QL0 or QL1, is another area of interest. So let's jump back into the Grand Canyon project for a minute. Here's a quick overview of the project. It consisted of 2 areas. On the right, you're seeing section 1, the base AOI, which is the Grand Canyon Central region. This includes areas such as the Grand Canyon Village, the North Rim, and the Kaibab Plateau. This is kind of your iconic, picturesque, postcard-worthy section of the Grand Canyon in Arizona. And on the right, we follow the Colorado River down to the west, where we have section 2, Grand Canyon West. This was airborne LiDAR acquisition. It required delivery of high-quality elevation data to USGS standards. It was kicked off in the fall of 2019, and it involved the support of several state and federal stakeholders. Typically, these projects have several agencies, both from the state and federal level, who are interested, who support the project, both financially and technically. And this project is now in the national map. It adheres to 3D standards and LiDAR-based specifications. The project was procured for a number of reasons, including dam safety assessment, engineering design and design reviews, habitat conservation research and modeling, because it is a national park, and there is some ecologically sensitive areas there. As I mentioned before, floodplain mapping and hydrologic modeling is of interest for the entire nation, particularly in Arizona, where we have monsoon season, and understanding where large volumes of precipitation will flow is of interest. We've also seen some severe fires on the West Coast, as many of you are aware. So understanding fire and burn modeling using elevation, it's a critical resource in hydrographic modeling and burn modeling. And lastly, integration with the federal LiDAR base map. So here's our second bar. I'm going to try not to bore too many of you, but I'd like to cover the basics of the science behind airborne topographic LiDAR. LiDAR stands for light detection and ranging. It's an active remote sensing technology. LiDAR uses laser pulses. So you have an emitted laser pulse from a sensor, and you time, because the speed of light is so constant, you can time the reflection of that light to come back to a receiver, where you can measure very accurately distances from the sensor, and you can place a measurement or a point very accurately on the ground. When you have many measurements combined or many points combined, you create a high resolution 3D image out of the LiDAR data. We call this a point cloud. Point clouds are used to effectively and accurately assess features and create geospatial elevation products. So if we look at the graphics, and I use some very helpful online sources to help illustrate this. In this case, there's a great video from Neon out there that explains the basics of how lidar works. So I encourage anyone who's interested to watch that video. So one, you have a lidar unit which scans the ground. You emit laser pulses. You have a mirror which oscillates or rotates to distribute those points over a larger area, and a receiver detects the reflection. Simultaneously, you have GPS connected to the aircraft or the rover antenna, and you also have a secondary GPS to correct for GPS error, often a base station or a satellite or a virtual base station as technology progresses to be able to place those points from their source, which is the sensor. You also have an inertial measurement unit or an IMU, which extremely accurately corrects for the roll, pitch, and yaw of the aircraft. And that corrects minor error in lidar point placement spatially. And you also have a data computer that records all this data, which is then calibrated and processed into products. One of the great things about airborne topo lidar is, unlike photogrammetry, it's not only very accurately vertically, so it's great for elevation mapping, but it can also, to an extent, penetrate canopy and relatively accurately measure the ground beneath canopy. So what you're seeing on the left side is a lidar pulse traveling through a tree and a canopy. Light will never penetrate a solid object, but you will get a portion of a laser pulse which reflects back and a portion that continues down to the ground. lidar experts are able to classify those ground points and use those ground points to create a ground macro, which allows for a continuous elevation product despite above ground features like vegetation. We use a number of laser wavelengths in lidar mapping. What you're seeing in the very bottom left is 3 of the most common wavelengths. You're seeing this green bar vertically is a 532 green laser, 532 nanometer. That's typically used for bathymetric mapping, as it can penetrate a water surface and create measurements of a lake bed or a riverbed. The reflection of light is why we use various wavelengths in lidar scanning. One of the most common for topo mapping is a 1064 or near infrared wavelength. That is used because, as you're seeing in this graph, the green line is reflection or reflectivity off vegetation. The brown line is reflectivity off soil. So the near infrared wavelength has what's called a diffuse reaction, where a beam of light contacts an object and the light reflects equally in all directions, so that even if you're not directly in the line of sight of the laser pulse, the receiver can still pick it up because the light reflects in all directions. Lastly, sometimes a fully infrared wavelength is used that typically allows you for identifying soil and mineral types. Back to the Grand Canyon. Here's a little bit on the specifications and deliverables that were required for this project. We did a classified point cloud, and classification is where each point, you have millions of points creating a 3D image, if you remember. Each point has associated metadata on what object that point is contacting. So that could be ground, that could be water, bridge decks, high noise, snow, temporal exclusions, overlap, or withheld classifications. Also from the lidar point cloud, we derive a digital elevation model, and I'll get into that in a little bit, at a 0.5 meter pixel size. We created a first return surface digital surface model, which is a raster product of which includes above ground features. We also include hydrographic break lines, which delineate land and water features. We delivered intensity imagery, which is an identification of the reflectance of the surface. So it's a metric, or it's a raster grid showing the voltage of the lidar returns, showing how reflective that object was. So it's great for identifying features and determining what those materials are by their reflectivity. This project also required a control survey, as well as standard LBS metadata and project reports. This data was delivered in 2022 and is now available in the national map. So here's some basics of airborne LiDAR specifications and products. Point cloud spatial resolution is the number of LiDAR measurements in an area. Typically, we gauge the resolution of a point cloud by points per square meter or points per square foot. So it's the number of LiDAR measurements within a defined area. We have nominal and aggregate nominal pulse density metrics, nominal being a single pass, single return metric. And again, a LiDAR pulse, even a single LiDAR pulse, can have multiple measurements. So in this case, we're looking at last return, which is typically the ground. So that's used for elevation mapping because we care more about the base elevation than above ground features for elevation mapping. And an aggregate nominal pulse density is the combination of multiple LiDAR swaths that are overlapping each other. A higher pulse density will drive product quality. So the more points you have, the more well-defined features are. That's important if you're creating downstream products like elevation models or surface models, or if you're extracting features. Average point density is another way to look at the spatial resolution of a point cloud, which is just the total number of points divided by the area. And we can also look at the point distribution or rasterized or other point densities, such as Voronoi point density measuring metrics, where we look at a grid of, say, a square meter, or we look at a tin model, which is a triangulated surface, and we look at how many of those cells meet the base point density requirement. So quality level 1 is a minimum of eight measurements in a square meter. Because we want 2 measurements to define an elevation in a raster product. So let's say we have a gridded map of your elevations. We want 2 points in each grid pixel to determine the elevation. So that's why 8 points per meter allows us to create a half meter pixel in a surface raster. The smaller those pixels are, the higher resolution quality surface product you have, and the more you can do with that, the more metrics you can pull out with a higher degree of certainty. Quality level 2 is the same, but it requires 2 points per square meter, so it's a lower resolution version. And quality level 0 is the same as quality level 1, 8 points per meter, except it has a higher accuracy standard. And you can see on the bottom chart on the right, the root mean square error in elevation, or Z, for non-vegetated and vegetated at the 95th percentile. These are in meters, so essentially quality level 0 is looking for an average RMSE Z of 5 centimeters or better, and quality level 1 and 2 are looking for 10 centimeters or better. We're also looking at pulse spacing. So this is the average distance between pulses. Some LiDAR sensors collect points with a poorer distribution of points. So quality level 0 and 1 are looking for 0.35 meters between points or better, and quality level 2 is looking for 0.7 meters or better. There's a few ways we can gauge accuracy of a LiDAR point cloud. One is absolute accuracy. We send out a field survey and we collect ground truth points, and we compare the LiDAR pulses to the absolute ground truth. We also look at comparing the LiDAR to itself relatively. So we'll look at the overlapping areas and produce a delta Z raster, which shows the systematic error in the LiDAR sensor and its as it compares to itself. So if you have an area collected with 2 strips of lidar sensor or of lidar coverage, you look at the overlapping area to see where it deviates from itself. Further, you can measure the precision or the smooth surface repeatability within a single lidar swath, where we're looking at where points deviate vertically within a theoretically smooth surface. We mentioned that a bare earth digital elevation model, a 1 meter product could be created from quality level 2 lidar, and a 0.5 meter product could be created from a quality level 1 or 0 product. A digital elevation model uses ground class to model the bare earth only. This excludes the above ground features. Conversely, a first return digital surface model includes above ground features. So we're using the first return versus the last return in the lidar measurement. Topo lidar, as we talked about wavelengths previously, topo lidar does not reflect well off highly reflective surfaces. We have what's called a specular reflection off, say, highly reflective tin roofs, mirrored surfaces, and water surfaces. For this reason, water does not turn out well from a topo lidar survey. We don't get full coverage on a lidar surface because of that reflection property. And for that, we create hydrographic break lines where we delineate land and water surfaces, and then we can enforce or flatten the water surfaces to take out some error because of those gaps in the topo lidar coverage. So when we're flight planning the Grand Canyon, there's a number of challenges. There's a massive elevation change that happens very drastically. Some of the taluses or cliff walls in the Grand Canyon will drop 5,000 feet over say a 20-foot lateral. So you have essentially a cliff face where the terrain changes very drastically. So that's certainly something to consider when you're planning a lidar collection. For that reason, we try to bring in existing contours and try to plan the flight lines along or parallel to the contours so that the range from the sensor to the ground is as consistent as possible, and you don't have a flight line where your lidar scans from a high elevation to a low elevation laterally. That's certainly something to consider. So that's where we select our altitude based on laser spot size and the minimum train heights. So we will bring in existing contours, existing elevation models, so that we can plug that into a flight planning software that knows how long a sensor can range. Essentially, as a laser travels through space, the energy in that pulse is being attenuated. So the laser can only measure so far before the return of the signal is so weak that you can no longer differentiate a lidar return from other backscatter noise, such as light from the sun. We call that the signal to noise ratio. And the result is dropouts. You don't get accurate lidar measurements if the laser is traveling too far or off a surface that is not reflective enough. Secondly, when dealing with very sharp cliff walls, it's important to have a little extra lidar overlap. And that's because you have when you double up a lidar overlap, let's say most projects, if you have a single lidar pass coverage where you're meeting your point density requirements in a single pass, typically you'll use 25 to 30% overlap with an adjacent flight line. If you're using 50% or more, you're collecting everything twice. And maybe I'm a lidar geek, but every time I cut the grass, I think about flight planning. When you think about it, if you're covering everything twice, you have a greater degree of angles to capture the sides of cliff faces. So in this case, we used a 55 or 60% lateral overlap with adjacent flight lines so that we're collecting more of those cliff faces with a bird's eye view scan. On the right side, you'll see our flight line orientation. We tried to orient them parallel to the contours of the area, which is rather difficult in the Grand Canyon. Also, vegetation is a factor. you have to consider that a lidar pulse needs more energy to travel through vegetation and get a valid range or a valid elevation point through vegetation. So you can't push a sensor to its max efficiency for that reason. I included a comical but very true quote from The Office where Dwight says, "Along the north rim of the Grand Canyon is a forest as lush as you've ever seen." And that's actually very true. It's the Kaibab National Forest, and WGI has mapped that area as well. So other things to consider when flight planning, it's very important to understand that in projects like this, delays will happen. Certainly, you're waiting for weather. You cannot collect LiDAR in rain, which isn't so much a factor in Arizona, but certainly fires. We did encounter forest fires that were blowing smoke over our project area, and that prevents us from flying. We also have to consider the reflectivity in the land cover, so the vegetation, and we estimate the reflectivity of the ground to select an altitude that is high enough to be efficient, which means you'll have wide LiDAR coverage, but not so high that you're unable to penetrate canopy, you're unable to get valid ranges in the bottom of that deep canyon. To further explain what I was getting at previously, you'll see in the top right an example of a 10% side lap where we have minimal side lap between LiDAR passes. We're covering everything once. But on the right side of that top right graphic, we have 50% side lap where it's demonstrating a greater diversity in the LiDAR coverage. And this is a parallel cross section of the LiDAR coverage. It's kind of, because you have a scanner distributing points, it comes out in a triangle shape. So you get a little bit of angle at the edges of the scan. Here's a little bit on LiDAR sensor parameters and what they mean for project planning. We have pulse repetition frequency, or PRF, also known as PRR, in kilohertz. So for example, 1000 kilohertz means you're firing 1 million pulses per second. That's also 1 megahertz. It's the rate at which laser pulses are firing. So a higher PRF means you have more points or better spatial resolution, but each point then has less energy, and you can't fly it as high or efficiently because of that attenuation that we talked about previously. The goal is to use a high enough PRF to exceed your specification with a little bit of buffer, or for your extraction needs. Quite often we'll over-collect pulse density so that we can automate feature extraction, which is a cost-saving capability for our clients because we use such high-quality LiDAR sensors. Scan frequency in hertz is the speed at which the scanner oscillates or rotates to distribute the laser pulses. The goal is to plan that with your planned speed of your aircraft to distribute your pulses evenly. We call this cross-track or down-track, and it's important to have an even distribution. You could have as many points as you need for your project, but if they're not evenly distributed, you still don't get a consistent elevation product. A scan angle or field of view is the maximum angle of lateral pulse distribution, so how far the mirror scans from 0 degrees or straight down, which is called nadir. A lot of sensors offer roll and swath compensation or gyro-stabilized mounts to correct for some of that aircraft dynamics, which causes quite significant amount of point placement variance. You kind of have a wavy flight line if you're not compensating for that. Again, we covered our 50% overlap, which is beneficial for penetrating vegetation and capturing the sides of vertical surfaces. This also doubles your nominal pulse density. And altitude and ranging is an important factor. Higher the altitude means wider LiDAR coverage, but lower density. And a higher altitude means greater pulse attenuation. You will have a larger beam footprint. So the footprint of a LiDAR pulse expands the further it travels. Even though you have a point on the ground, the actual light source is often 0.5 meter to 1 meter wide. And that point is being placed in the middle of that laser footprint. So horizontally, if you're able to capture a point on the edge of this footprint, it creates a little bit of horizontal error. So a tighter lidar beam divergence or a smaller beam footprint is often a good thing for accurate point placement. So I mentioned that the Grand Canyon is a particularly challenging project. When we're starting these projects, we're estimating how long it's going to take us and how much it's going to cost us to perform this work. If you don't understand the challenges up front, it's going to result in delayed projects, overrun budgets, and just a miserable time because, again, from experience, things always come up. So having the experience to understand the challenges up front and tackle them in the most cost-effective way is critical for any large-scale elevation mapping program. In this case, we had to lay lidar control points. So we have to send in surveyors to meet lidar base specifications to collect lidar control points, which we use to calibrate and adjust the airborne data. We also collect a wide range of checkpoints, which we provide to the third-party QA, QC department, and they check our lidar accuracy against that ground truth. At the time, we've since done away with this, but at the time there was a difference between a non-vegetated checkpoint and a vegetated vertical accuracy checkpoint. So we had to collect both vegetated and non-vegetated survey. Now that sounds easy. We send a surveyor out, they drive around, and they collect your points before you go fly. However, with the Grand Canyon, that presents a lot of challenges, particularly for just land access. Because we need to distribute these survey points, we can't access a large amount of these areas. So we have to think, what kind of vehicles do we have at our disposal? Where are the existing roads, trails, routes where our crews can get? And what we did to assist in this process is we leveraged our GIS experts at WGI, and we created a layer of all the existing roads, routes, and trails. And we overlaid that with the most cost-effective solution for a ground survey plan. We do this planning upfront before the project's even awarded. And we look at how much it's going to cost to survey this. So we brought in several GIS layers, and we determined that with the existing routes and the vehicles that we have available, we needed helicopter access. In this case, we actually had to fly in with a helicopter with support of several state and federal agencies, a helicopter access where we actually had our crews dropped into the canyon from helicopters so that we could collect that necessary survey. We're also thinking about land access. Who owns the land? You know, with privately owned land, we have to get permission to access this land. And in this area, there's a large presence of tribal nations. So we have to get access from, in this case, National Park Service, the GCRA. We had to get a GCRA backcountry permit. We had to talk to FAA to get airborne access. And we had to coordinate with several state and tribal organizations to provide the permissions to access these lands just for our control survey. If we didn't do this up front and estimate the time and budget that it would take, this project would have gone quickly off course. There was also a large ecological and habitat consideration to consider upfront. There are national wilderness areas, which we also mapped upfront in our GIS process. These areas require permits to access. And also what you're seeing on the right is all the existing nesting locations of two protected species, the California condor and the Mexican spotted owl. When coordinating with our backcountry permit and the National Park Service, we were advised that our land survey firms could not be within a mile of these known nesting sites. So when you combine that with all the routes, where can we actually physically access? Where do we need a permit to access? Where do we need permission to access? And where are we restricted from going? It actually creates quite a complex issue that requires upfront planning. It certainly can be accomplished, and we did accomplish it so that this project stayed on time and on budget. Our land survey also requires physical documentation, and I'd like to share this with you because I used to be a field guy myself, and these pictures make me miss the field work. In this case, we're seeing some of the static and RTK survey collection activities, both for our assessment and our control survey. We're seeing in the bottom right the helicopter that had to fly our groups in, and it certainly provided some stunning photos. Of course, these areas need either satellite or cell reception, and they require a relatively flat land. As well, the non-vegetated and vegetated areas require, what they sound like, non-vegetated or vegetated regions. So all these areas have to be identified up front. Here's a little bit on the products. So what you're seeing in the top left is our lidar point cloud. We did a pilot first to sort of prove the sensor parameters, prove our capability, prove that this could be done. And in this case, we co-collected RGB imagery. The great thing about being able to collect lidar and imagery simultaneously is not only can you can leverage the vertical accuracy of the lidar and the horizontal accuracy on features of the photogrammetry to produce a corrected and very accurate product in X, Y, and Z. But you can also assign your lidar points a true color pixel from the imagery. And that's what you're seeing in the top right. This is actually a 3D image made up of millions of lidar points, and they're colorized accurately from the camera. Top right, you're seeing your point cloud. In this case, this was a quality level 1 project. As we get to more recent lidar elevation mapping projects, we've moved to a higher standard of lidar collection. So we've moved to quality level 1, or 8 points per meter lidar point clouds. And this is because of a growing need for more precise, more accurate, and a higher resolution product. Like I said, a QL1 product allows for a half-meter digital surface model and digital elevation model. So that's what's driving that. In the bottom left, you're seeing our hydroflattened and non-hydroflattened bare earth digital elevation model. So this is a raster product where each pixel is half a meter of the ground, and it's colored by elevation. And then we zoomed in right at the Colorado River to show what that looks like. These are some of the other lidar deliverables. In contrast to the bare earth digital elevation model, there's the first return digital surface model, which does include above ground features. Again, 0.5 meters because it's a higher standard of lidar point cloud. This is another zoomed in picture of the Colorado River showing a hydroflattened water body. And you can sort of see, it's a little faint, but you can see a lime green boundary that we've inserted showing the delineation between land and water. Those are our hydroconflated break lines. Bottom left is what the intensity imagery looks like. Again, this is another raster product that is generated based on the voltage of the signal returned back to the lidar receiver. And that shows a grayscale of the reflectivity of the surface. So light is absorbed by darker colors, light is reflected by lighter colors. And that's where you can use lidar intensity as a help, maybe not the entire solution, but as an assistance in identifying what features are. So here's some of the results from the project that was delivered and included in the national map in 2022. Our lidar points. So you'll see if we jump back to the lidar-based specifications, the aggregate nominal pulse spacing requirement was 0.35 meters. Our points averaged 0.29 meters between each other, and our aggregate nominal pulse density which required 8 pulses per square meter, we achieved almost 12. So again, we collect a little extra buffer so that it ensures we don't have to go back and collect again. These are hard requirements. They're well defined. They're being checked, and they're being used for public consumption. So it has to be right, and the cost of flying it twice is just too extreme. So we tend to over collect. If we look at the checkpoint accuracy in meters of this data set, our non-vegetated vertical accuracy assessments, we ended up with about 7.8 centimeters vertically, averaging on the non-vegetated. Again, the requirement is 10 centimeters. And our DEM also achieved the 10 centimeter requirement at the 95th confidence level. So let's cover some of the key takeaways from this webinar. Projects require a customized project management approach. We have found we've done a lot of these large area elevation mapping projects. Each one of them is different. As Americans, we're extremely lucky to live in a very diverse geographically and topographically country. So projects are very, very different. Vegetation has to be considered. Environmental factors have to be considered. Land access has to be considered. And we have to have a great understanding of the technology in which we're using so that we don't run into dropouts or sensor issues. And there's a lot of things that can go wrong, and that's why this type of work really is a professional service. It requires certified professionals, and it requires a lot of experience. We're very proud of this project, not only because it's one of the 7 natural wonders of the world, the Grand Canyon. It produces some really stunning data, but it's also the first quality level 1 lidar project for this national park. So we've stepped up the quality, the spatial resolution of the data. And it's also one of the earlier projects where we as a country and our federal agencies move towards a quality level 1 update of data. It's also the first multi-agency collaboration for aerial survey of the national park. This involved several state and federal agencies all collaborating. So it was a really, really rewarding project to pull off on time, on budget, and to specification. As we close out, I'd like to take you through, again, I'm a lidar geek myself. I hope there's some lidar geeks out there who are going to enjoy this this fly through of the lidar point cloud over the North Rim. As you can see in it, this is a single pass of lidar. We're capturing the top and about 3,000 feet down to the Colorado River. So it really demonstrates the importance of a high level of lidar overlap and an accurate understanding of the project specific environment, so that you know you're going to get point measurements all the way down to the bottom of that canyon. And for the sake of time, I'm going to move on here. Again, I'm going to give you a second to scan this QR code. That's where you can access the white paper. I encourage all of you to ask questions, reach out, download the white paper, and learn a little bit about why elevation mapping is so important, and the challenges that are involved for the consultants that perform this work. Thank you very much. I appreciate your time. I hope you had some lunch while we were doing this, and I think we have about 10 minutes for questions.
Great job, Mark. Guys, if you want to drop your questions in the Q&A section, we'll read them off to Mark and he'll get some answers back for you. Mark, I think we got one here. Is WGI working on any other QL1 LiDAR projects for any additional national parks?
Yes, we have done We have some in the works for other national parks. We've done work in that area at QL1. I believe it's for the U.S. Forest Service. But over the years, certainly we have done national parks. I'm thinking of some national recreation areas and some other national parks. We've done, a good one comes to mind is White Sands National Park. We've done that several times. It's an annually recurring project. That one actually won a MAPS Project Excellence Awards, People's Choice Awards several years ago. And if for anyone who's familiar with White Sands National Park in New Mexico, that's another area we've done several times. So what we do, it's essentially an area of sand dunes that shift quite regularly. So we do an annual temporal collection of elevation data for that region. And it's particularly interesting because several years ago, archaeologists found fossilized human footprints from very early hominids in White Sands National Park. It is near a military and missile range, so it was lucky that the archaeology was preserved. And it's quite interesting because that area used to be a lush, forested and there was a lake that was in New Mexico thousands and thousands of years ago, if not, yeah, thousands. And a lot of people live there. We found saber-toothed tiger remains in that area. We found woolly mammoth remains and humans. So it actually, the discovery of that archaeological site challenged what we understood about migration of early humans to what is now North America. We were able to carbon date some seeds that they were carrying, and there's some really interesting National Geographic articles on White Sands. And that is an area that we collect every year for the temporal change detection of those sand dunes.
I think we got one more in here too. Can you comment on the timeline to complete the control point check point collection effort?
Yeah, so the control effort is mostly planning. We had surveyors out there for a couple weeks, but we're talking months of planning, making sure there's the right weather, making sure we have permits lined up, and making sure that that we have permission from tribal organizations. So this was probably 6 months of planning and coordinating that control and a week or two of actual field collection. The airborne field collection, I believe, was 10 days and like a year of planning.
All right, does anybody have any additional questions? You drop them in the Q&A section. Give them a minute here, and if not, we will call it. Doesn't look like anything's coming in here, Mark, and we're running out of time, so I think that's going to call it.
All right, I guess I covered everyone's questions in the presentation.
Thanks so much, guys.
Thanks, everyone. Have a great day.